Hi everyone, my name is Lydia and this is what I wish they taught me about econometrics and introduction. In the previous video, we worked an exercise to find out whether a given estimator was biased or unbiased. So in this video, we're going to move on to precision, why it matters and why unbiasedness is not enough. This time, instead of the expectation operator properties, we're going to put into practice our variance operator properties. So let's move to the exercise. Let's consider the model yi equals to beta null, beta 1, xi, epsilon I. And we've got the conditional expectation equal to 0 as well as a constant variance, meaning homoscedasticity is satisfied for this case. Suppose we have two estimators. So we've got the usual beta 1 hat coming from the OLS. Keep in mind, this is the same beta 1 hat for which you know the formula for. And then we've also have beta 1 hat plus CZ, where C is just a constant, different from 0. Z is a variable for which we've been given information, such as the expectation of Z is equal to 0, the variance is bigger than 0, and it's independent of everything else, meaning the X or the I that we have in this expression. So let's figure out which is more efficient out of the two estimators. As a first step, let's very quickly see whether these estimators are biased or unbiased. Well, in this case, we'll know that both of them are biased because the exercise was built so that you can check the efficiency, but let's also do a quick revisit to what we learned in the previous exercise and do that quickly. So keep in mind, because we've got here the conditional expectation being fulfilled, that means that the expectation of our beta 1 hat is going to be equal to beta 1. For the second estimator, we've got the expectation of beta 1 hat plus CZ, which is going to give us the expectation of beta 1 hat plus C times the expectation of Z. And we've been given that the expectation of Z is 0, so the entire expression is also going to be equal to beta 1, which means, yes, both are unbiased. Before you look at the solutions for the efficiency, pause the video for a moment and try to do the math on your own. Once you've given it a try, come back and compare the results with what you see in here. So now that we know the two estimators are both unbiased, let's check the one with the lowest variance, and that is the one that we're going to keep. So for the first one, we're going to have the variance of beta 1 hat, which ultimately is just the expression that we all know for the beta 1 OLS. We don't need to really write it in here. Let's just keep in mind it's just the variance of the beta 1 hat. For the variance of the second operator, however, we've got beta 1 hat plus CZ, and that's where we're going to apply the properties of the variance operator. This is going to be the variance of beta 1 hat plus the C, keep it, was a constant, so it can go in front of the variance operator, which is a quadratic operator, and we'll have C squared variance of Z. Keep in mind, C was different from 0, so it means that C squared is going to be a positive number, regardless of the C being positive or negative. And we also know that the variance of the Z is a positive number, so ultimately we have this entire expression being something that is not 0. Which means at the same time that the variance for the second estimator is the variance of beta 1 hat plus something positive, which will mean that the variance, let's call the second option be like beta tilde estimator, is basically bigger than the variance of our beta 1 hat estimator. What does that tell us? Well, it means that even though both estimators are unbiased, the OLS one is the one with the smallest variance and the one that we will want to choose to work with because it's more efficient. So this exercise is supposed to give you also a key takeaway, which is you cannot improve an unbiased estimator just by simply adding noise, even if that noise has a zero mean. So that noise being the Z in here, which had that zero mean. Unbiasedness only tells you you're centered on the truth, but efficiency tells you how tightly you cluster around it. Okay? So OLS, in a sense, is not wasting any of that information. There is a connection here also to the Gauss-Markov assumption or theorem, because in a sense, it's also a preview of the theorem itself, because it says among all linear unbiased estimators, remember, OLS has the smallest variance. And again, in here, the variance of the beta 1 hat was indeed the one with the smallest variance. So any other linear unbiased estimator is just OLS plus some extra noise. Bottom line, when you compare different estimators in any of the exercises that you might see, first check the unbiasedness, then compare the variances just like we did in our 2 videos. And then if unbiasedness is not enough, precision is the one that is going to help you make the final decision. In the next exercise video, we're going to move a little bit from the algebra and concentrate on which OLS assumptions fail for certain situations. So I'll see you in the next video.